Welcome everybody. So sharing with us his ideas and the excitement of his interesting research is Zhenhuan Yi. Zhenhuan has graduated from Chirped University, and it was some time ago. And in my time as an undergraduate student, I'm not sure I even heard about the Nature journal. While Zhenhuan has published a paper in the Nature journal as an undergraduate student. And I looked it up this morning. The citation of this paper is somewhere around 400. And I like the title of this paper, of course. Experimental free space quantum teleportation. It's nice. Experimental free space quantum teleportation. So if you were wondering who is responsible for this field, of course, since then, we had a pleasure of having Zhenhuan as a graduate student here. He got his PhD from A&M University. And he built a lot of interesting experiments here, a lot of thoughtful research projects wouldn't have been possible without Zhenhuan. So today, as I said, he will be sharing with us his ideas about opportunities in laser plasma interaction experiments with high power ultrashort laser pulses. Zhenhuan Yi, professor of physics, associate research professor at the Physics and Astronomy and the IQSE of Texas A&M.
Yeah. Well, thank you for such a generous introduction. I mean, while I was preparing this talk, I had first to have made some disclaimers. I mean, very few of the work presented here is, only very few of them I was directly involved. I mean, so to facilitate a discussion about how to use these these really good systems. So we put up this talk. Many work is from Dr. Sokolov and Scully and University. I was thinking of a particular word, instrumental. So we can say I'm playing an instrumental role here, or to facilitate the success of this maybe a program or something with these lasers. So let's keep going and see what they are. So it's hard to list everybody contribute to all these different projects. So I decided to only list those who directly involved in these projects. So many of them are not here. A few are here, but there are many interesting works that can be continued from several lines. Later you'll see. So this is the lab in Baylor. We have a few sessions or big rooms, and we're talking for this talk. We're in particular interest of this session of the lab, which has high power picosecond and femtosecond lasers. This was old, those femtosecond lasers here. And then some vacuum chamber, which facilitates the plasma experiments. And this is the main workhorse for many of the projects here, showing in this talk. And this is a near-dimming Yak laser, no-lock Q-switch, no-lock laser, picosecond pulses. With here, this is the oscillator, and then the amplifier, and on this end is here the OPO and different frequency generation unit. And On the other end of the table, there's this vacuum chamber which facilitates the plasma exchange. And a more recent photo is shown here. This is the picosecond laser system. And then here is the new installed femtosecond system. You can see this is the oscillator. This is the femtosecond system. And the oscillator, the pulses from the oscillator has been split in two parts. One part feed into the femtosecond system. The other part went through a very special piece of instrument. I'll talk about that later. And see the amplifier here. Now this picosecond oscillator is not in use. Now the whole system is seeded by a femtosecond oscillator. And then all these pulses, right? They propagate down these long tubes in order to isolate electrons and send into this chamber, which indeed will be kept in low vacuum. And when it's working, you can see this is a jet nozzle. When air, for example, nitrogen or methane, coming out of this slit, it shoots out, and then a laser hits it, heat it up, and ionize the gas and forms a plasma channel. So the first thing you want to know is like what are the specs of this laser, and you can read from here. This is the femtosecond system and the picosecond system. The pulse duration is about 60 picoseconds, and its maximum repetition rate is 10 Hz. Of course, you can dial it down to like sub-hertz. And the pulse energy is listed here. And it also has OPO, this OPO and different frequency generation. The wavelengths can extend all the way to.
So when you give 3 wavelengths,
yeah,
2 wavelengths, 3, is that because you have those systems all laser, or is it because you've got parametric oscillators in there?
Oh, this one is the parametric oscillator is here.
I know,
Let me go from here.
Yeah.
This is the fundamental. This is the fundamental. This
Right.
is second harmonic and third harmonic. You have to send the fundamentals through.
But are they all lasing? Are they all above threshold?
Yes, they are all laser. These are all laser pulses
Okay.
at 10 Hertz.
Right.
This is a pulse energy. This is
Okay.
pulse energy.
Right.
Yeah, so the whole system is like 4 watt. And then you can also send this 355 into the parametric oscillator. Now this one has to go, this pulse has to go through a crystal. And then, of course, this is several stage. You first seed it from spontaneous process and then amplify it in the second step. And the wavelength is tunable depending on the crystal end and timing. You can tune from here to there. And then you send part of the beam. Not that part I forgot. Part most likely this beam, and some of the tunable beam into a different frequency journey. And then that will, by different frequency process, this is another crystal, you generate close to mid-infrared. And then the femtosecond system, it's right now it's at 40 femtosecond, up to 1 kilohertz, and you can also dial it down to match the frequency of this laser. And then right now it's there, 7 meters and per pulse. So both lasers now they are synchronized with picosecond time jitter. And this part of the work was done by Zhenfei, which is here, and well, Ben Stryker. This is a measurement, but Ben and Zhenfei constructed the measurement setup. So now this is the special piece here, the photonic crystal fiber. You might be wondering, how can you gap from a femtosecond pulse at 800 nanometer? Yeah, see, 800 nanometer. This the laser pulse, femtosecond pulse at 800 nanometer. The amplifier only works. Is near the yak, right? So it only works for 1064 picosecond pulse. How can you gap that difference, right? This piece of photonic crystal fiber comes from the work of Dr. Jotico back in 2004 or 2004. And this work, I mean, it takes really short time, right? I mean, once they get this work done, A-Plus basically bought their patent and then commercialized this piece of commercialized this instrument.
Well, I wanted to understand this better.
Yeah.
It's a nice talk. Thank you. What is it that is so wonderful that we owe to our distinguished colleague? Count me again.
So this fiber is able to convert femtosecond pulse at wavelength 800, right?
Right.
When the pulse propagate down this fiber through Raman process, its wavelength shifts toward the red end to 1064, while this soliton also stretches in time. So once the system was built, then the next thing you want to find out, like how stable the time jitter between the pulses are. So what you can do is to take this femtosecond pulse, and by just simply passing through a wedge, you can pick up two femtosecond pulses, and the relative delay between them will be very stable, since they come from the same pulse through a solid piece of glass. And then send all the three beams, right? Automate them, send them to a street camera, and then look at the statistics of these three pulses. So when you look at the time delay between the first two, so the jitter is most likely contributed by the instrument itself. We're using a street camera to record the pulses. So you take that, take this 170 femtosecond jitter as the instrument jitter, and then later then you do a lot of feedings, right? Thousands of samples, and feed for this time delay, and then look at the statistics. This number has already subtracted this instrument jitter. So that means like the picosecond pulse is quite stable. I mean, in terms of timing compared to with respect to the femtosecond pulses. We're not exactly sure where does this jitter comes from, most likely from the amplification process, or it could even be contributed by the detector itself. Because of intensity fluctuation. But this is the specs of the system. Coming out of the laser, we have femtosecond pulse with time duration, full with half maximum, about 38 femtosecond, and the picosecond pulse is more precise, right, compared to the specs is 60 picosecond. So what do we do with this system? The original plan for this whole system was to use it for water window X-ray lasers. And also there are other purposes uses stimulate Raman amplification process in plasma, as well as I think this serves as this aim serves for both experiments.
Okay, can we go back a sec? So, when you talk about guiding in extended plasma channels, you're thinking about the Princeton problem, not filamentation.
Not yet.
Okay.
We will come to filamentation first. So a few slides about the X-ray imaging, and as we know for X-ray imaging, we're actually using hard X-rays, and shown here. And then what is this soft here? In this region is soft X-ray, can be produced by electron process. And then in this particular region is called water window. Why is it interesting? Because in this region, you can use that to image in softer tissues. This is absorption. I mean, this curve here is the absorption in water. This is May absorption from oxygen in water. And then, but for protein, the absorption is less. I'm sorry, the absorption, the absorption is less. Oxygen absorption increases here. This is the edge, right? But in this particular region, like carbon and nitrogen, and this is a little peak on protein. These are 3 peaks: carbon, nitrogen, and oxygen absorption from protein. So there's now here you see a contrast from water and protein. And use this, you'll be able to image softer tissue. And then the way Dr. Sukeva from Princeton proposed to generate coherent X-ray, soft X-ray pulses is to use hydrogen-like atoms or helium-like atoms. In this case, it's a hydrogen-like atom. So this one, the carbon, this is a carbon 6 because it has charge 5 with 1 electron and the nucleon. And this is a work from 10 years ago. But this source is not coherent source. This is a plasma source. When you focus a very strong laser into a liquid jet and form a hot plasma, and then there will be incoherent soft X-ray. And then you can use crystal optics to collect those soft X-ray and then focus them on the sample. And this is a tomography of a kidney cell. So the scale bar, there's 3 micron, is 3 micron. Okay. So, yeah. And there you can see many structures inside the cell, which comes from, like we previously said, the nitrogen and carbon atoms. And then this is another example using soft X-ray to image a infected blood cell or changes after it's infected. Of course, I mean, even for this one, the resolution is actually not that high, right? Even though the lambda is like 2.4, but the resolution is not as high. This is most likely because of the light source cell is not as tight. So that gives a spread function to the imaging system.
I don't understand. What's the cause for the spoiled
This
resolution?
is not coherent source.
Okay.
So it coming out from a large area,
Okay.
the light itself.
And the large area is very incoherent.
Right. It's incoherent, so
Okay.
it reduces it adds a large point spread function to
Right. Good.
the imaging system.
Thank you.
Yeah, so the resolution is still like 100 nanometer. That's why it's interesting to produce something like a coherent source, so that you can further enhance the resolution.
That's an interesting point. If you go to the doctor's office and he uses X-rays to look for bone fractures and so forth, what kind of resolution do they get relative to the wavelength?
That's a good question.
Yeah.
I never really looked at, but it doesn't really need very high resolution there. Even millimeter, I think, is acceptable, as long as you can see where the bone is, and the operation won't be that accurate anyway. Maybe if you use machines, maybe they can do a better job, but I don't think by hand you can even correct the fractured bone to a micrometer resolution.
Right.
And they use hot X-rays, something like 50 keV energy, photon energy.
Yeah. We were asked, Dr. Scully was asking the resolution achieved with hard X-ray imaging.
Incoherent hard X-rays. It's less than Rayleigh by a lot, and it probably is hundreds of times less. We just don't know.
About 1 million times less.
You think it's 1 million? That sounds awful.
Okay. The way Princeton goes, the approaches Princeton take to generate these ion 5 or ion 6 ions in plasma is to create like plasma channel, use gas jet, then send femtosecond pulses to heat it up, or to ionize it to heat it up, and then the population inversion is obtained through collision process. And this part I already remember. The key words I remember from Dr. Shapira's talk was that this process is not, this collision, right, the combination is not provided by 2-body collision. It's 3-body collision, because you need another particle to take away the momentum in that system, so that it can form a stable ion. And that's where you need high density. That's where you need high density. Otherwise, the 3-body fusion process is very rare. This procession is very small. So
what's this population inversion experimentally demonstrated?
yeah, we'll see in the next slide. So this is their experimental setup. It kind of simple, right? You have a chamber, and then this is already spectrometer. This is your probing. This probing goes here. This is just for detecting the channel. Right? You have another beam here. You have another beam here going this way. Also, that's just for monitoring this plasma channel. The main experiment actually comes from here, this beam. You just send it in and look what you get. But of course, you need to first create a very good plasma channel to just even start it, to get it started.
But you keep saying plasma channel, but it's not obvious that you would ever create a plasma channel. It isn't that we started out to create it. It's that we found out later on that we were getting it, and we attributed whatever enhanced excitation to the presence of that channel.
I'm not sure. I think they purposefully creates the plasma. There are more slides.
Well, that's something we should look into.
Where is Exicon here?
This is Exicon. I'm not sure if it's used for.
Not this one.
Oh, you mean? Well, it's not it's not even plotted here. That's a, I think this is simplified for just look at this X-ray process. Once the channel is created, ionized, then you send in this to look at what's been generated, and then that's the plasma channel. That's the plasma channel. The measure. This is from the side. This is a side view. What happens is you send in a coherent beam, right, propagating this way, and then here you break the wavefront and make them cross and make an interference pattern. And then if there are any turbulence, right, if there are any turbulence or change of reflect index in the pathway, then it will be reviewed in this interference program. So this is what you can see, that this is a plasma channel, which the reflect index is different from just plain gas. And this is another view, right? This view comes from this probe. This is a head-on probe of the channel. Then you can look at how, by looking at the profile of this light coupled into the plasma channel, may be able to guess, maybe able to make some estimate, like how you can improve it, or okay.
What actually is it doing? What actually is it doing in that plasma channel?
Oh, this is just like just to show that first the plasma channel is there, right? And
Yeah.
then the quality is not very high because the probe being coupled into it, right, is, I mean, it has a lot of modes in it.
Yeah.
But you mean, who cares? Why do you want a plasma channel? Is that what you're saying?
Yeah.
Right, that's a good question.
Yeah, that's a good
And
question.
and he's going to answer that in a minute.
Okay.
The
So-
answer is to get the population density up.
Oh,
Yeah, here, let me see, where should I start with? So let's go back one more slide here. So the purpose is to first to ionize carbon. To ionize, use very strong pulses to ionize carbon, and then create enough density of this electron density, both electron density and the bare carbon nuclei.
Right.
And then while they are recombined, right, this can produce the needed population inversion in some of the higher levels in this hydrogen-like carbon ion, which is carbon-6. So, and then here, this is the result I think published, right, about 2 years ago, showing that indeed there is 4 nanometer and another much more clean laser. Okay. So of course they also point out that the propagation, the channel quality is still not very good at that point. I'm not sure where we are right now. This experiment haven't been, there's some gap, I guess, during the COVID. So now come to another question. Like,
Could we pause? So this is the end of it. Go back to the last view graph. This is the end of a beautiful story. This heroic effort on behalf of Secaver to create X-ray lasing in the 100 nanometer range is succeeded at Princeton. But now Secaver is leaving. All these people are gone, and the apparatus is going to be maybe brought to Texas A&M. I say maybe because somebody has to love it. And we've got excellent people here who are overcommitted already. But we've excellent people out there that haven't made themselves known yet. And when you decide that you want to be famous, not just get a PhD, but make him famous, drag him along with you, make this whole progress work at Texas A&M.
Yeah. So, and if we go back to see the required intensity of these lasers, right? You find that it's really high. Like, we want to couple such a high intense laser into the channel to generate the X-ray. So let's come back to the high power laser. This graph talks about the power that's achievable by lasers and the free electron lasers by harmonic generation. So you can see that on this panel, right? Typically for many materials, damage threshold is a problem. Like most of solid material, like I think gigawatt, you start to get very strong nonlinear effect, and you go above that, like 10 times or 100 times above gigawatt per centimeter, most of the material will break down, they'll be damaged. But there are these quests, right, to reach these Schwinger limit, but they're not quite attainable using the
But
techniques.
we might tell my friend who's saying, what's the Schwinger limit?
Yeah.
Right? Schwinger limit is where the vacuum breaks down, where the field is so strong that electrons become positrons, or positrons leak out from the full Fermi sea that we picture in the Dirac equation.
And what's the current way, right, to producing? I mean, these these petawatt. We know now there are many systems around the world produce petawatt laser pulses. So the first thing you can do is to expand your beam, right? While you amplify the pulse, you expand beam, and then later the focus height. But that's not enough. Then what can you do else? You can expand in time. And that's the basis, that is the base for a Nobel Prize, right, in 2018.
Texas A&M.
So what you can do here is to first stretch the pulse, and then amplify that pulse, and then compress it back. But of course, there's a limit here. It's like, what you want to compress this back, what can you do to compress it, right? You are using the grating to do the compression. But while the grating here is relatively safe, right? When all the light comes to a smaller spot on this grating, that can create a problem. If the peak intensity is high, this grating can be easily burned. There you still are limited by the material. So to overcome that, there was this work saying that, hey, why do we go that route, right? We can use something that cannot be destroyed by intense laser. For example, a plasma. And how do you do that? Like, for example, you can send, well, inside a plasma, this is talking about inside a plasma, you can have a pump in coming one way and the seed pulse coming the other way. And through a stimulated Raman process, the seed pulse can take energy from pumping and get amplified. So since then, I think over the now it's like more than 20 years, people have been working intensively in this field and trying to push this process to above, there should be some threshold to make it really efficient. Right now, the conversion efficiency is quite miserable, I should say. Okay, before we jump into what has been done in that field. Let's talk about the plasma generation. Or how, when you focus a pulse, when you focus a ultrashort pulse, how does a plasma channel forms or so-called filamentation process goes on? So this picture says about all the key ingredients in this process. The first thing is a self-focusing process. And then when the intensity is really high, you rip electrons from atoms, from molecules, create plasma. And this plasma serves as a negative reflecting index, and then defocuses the light. And then, of course, the intensity is still strong enough to focus back. This process can go on, or it might create like a balanced process, like then you form a channel. So here, what happens is like you use some pre-pulses going through the axis, then the beam process and forms a vessel beam in this channel around this area. When here at the nozzle, the gas is you get the gas sheet coming out, and then this axicon, this vessel beam will ionize the gas and form a channel. And from there,
Plasma expands. That's the part of the story. Takes 1 nanosecond to expand, and as a result, you get lower density in the center than on the edges. And because the refractive index contribution of plasma is negative, you get a positive guiding in the channel that has this blue shape.
And that enhances the channel.
Yeah, that's how you obtain focusing by plasma.
This self-focusing, really start from this paper, self-trapping from Thompson. And a year later, Paul Keller, I think he was I'm not sure if he's postdoc or scientist. But this paper, also both are in physical review language. Is that like here is a beam. This is called Towns beam. It's actually called Towns beam. This is like a stable way, and it's self-trapped. It doesn't expand nor it shrinks. So there are also regions when this beam just focuses by itself. When the intensity is really high, inside medium, this curve effect really focused the beam. And by that time, he already mentioned that into something like this. But I'm not sure what he exactly meant for this. So
I knew him, and I know what he means.
okay, well,
He means he doesn't have a clue.
so I think really like 3 key ingredients can start the process, but there are a lot more to this filamentation physics, right? The first thing is like the Curry effect. When the intensity is really high, this Curry effect, right, is the third order nonlinearity. The intensity itself can form a Kerr lens to focus the beam itself. This is the first ingredient, right? But at some point, it will go to a singularity if there's nothing to stop it. On the other hand, when the intensity is very high, right, this multi-photon ionization can happen with a medium for an atom, or the tunneling. But of course, like depending on what media it is, like for example, in air, this process turns out to be negligible. So people mostly just talk about this in gas phase. So multi-photon ionization is more important, producing the ions. And so once the plasma is produced at some point, right, around the focal. Then this plasma has a negative refracting index contribution, which can expand the beam. So these are the, I think these are the three key ingredients in this process. And then there are a lot of terms. This is from a review paper in 2007. They start pointing to a lot of different effects. And I just took out a few. So there are a lot of different terms, right? Can be added to that long equation. Otherwise, you can just use, I mean, the simplest one, just counting the three terms, the previous three terms. It's just this simple equation. But you can keep adding a lot of different terms to it. So this process, when Princeton carry out this experiment, they use many pulses, just like Alexei was mentioning. Some of them were used to create the plasma channel, and then wait for the beam to expand, for the channel to expand, but before you send in the May pump, for it to be guided inside the channel. And then you also need to time this seed to collide with the pump inside the plasma channel. So this is the density, this is the electron density profile inside the channel. And yeah. So that's what I think. And the result, they were able to amplify. They were able to amplify for two different configurations. I think the pump energy was different. This one, it seems like there are like 10 to 30 millijoule pump pulse actually coupled into the channel. And then calculate the raw efficiency from this amplified femtosecond pulse to the coupled in the energy actually coupled into the plasma channel. This is the efficiency, about 9%. And then this is another set of parameter which the pump is reduced. But I don't know, like they didn't measure or couldn't measure the energy there. But the raw efficiency from here to there. This paper, what they did was they tried to look at all the parameters that are used in all these experiments. These Raman or Brion amplification based plasma. And then they found that there's a parameter range that seems like most systems would converge to. This A is the pulse amplitude, which is the intensity of the pulse. And then the other two parameters was grouped together. This is the coupling strength, and this is the pulse duration. So
is he talking about backscattered Raman?
this is backscatter Raman. They're talking about backscatter Raman. And then they try to collect all the experiments done by that time and compare all the conditions here. Like this slide is from Ben. So here, all these experiments are done in Princeton. And
Like
there are
the Caver's experiments or somebody else?
Yeah.
The Caver?
And then you can see there, the efficiency is actually quite high, especially these two. And then the conclusion from that paper, from this paper is that this line, this particular line, multiply all these parameters together. This all the three parameters together, right? There is a constant line, which is correspond to about 3.4, which is about 3.4. If you reach that number, it seems like you can get a quite good conversion efficiency. Many other experiments just failed to achieve that. And the efficiency is not very. So, and this was also, they also confirmed this in Brion Brion amplification. And but I never run the simulation or read into the details. But it seems like it seems like to be some clue there. And this only according to that analysis, right? For all those work, only these two work, only these two experiment, like right on this line.
So where are those done?
These are Princeton's. So there's a hope there. Okay, but of course, now here is the point. This is where our current system stands in terms of pulse duration, pulse energy. So the pulse, all these pulses needs to be stronger. So, okay, now coming back to some experiments actually done with the system we have in brick. This is a very early work, I think maybe 6-7 years ago, when this is 532, and this is the pulse from the amplifier. This is another pulse from the oscillator, from the parametric amplifier. And when you tune then to the vibration frequency of nitrogen, you can clearly see a lot of coherent Raman sidebands generated. And then later, Ben want to investigate how the system. I mean, this is the system we just talked about, right? Synchronized system, femtosecond pulse and picosecond pulse, and then send the pulses, synchronized pulse, into gas liquid cell and look at the amplification process. And this is some of the result. This is a log scale. Right? This is logger scale. So from here you can see that in gas, inside a gas, right? This is a methane at 3 atmosphere. Pump Stokes, and you can see there's a very strong amplification in gas. You can see it in counter-propagating process, very strong amplification. But the bandwidth is narrow in gas. This is work in another factor that clamps the further increase of this amplification process is like at some point the higher order start coming. The higher order Stokes start being generated through the amplifier. And in liquid experiment, then he made a cell, put in isopropane alcohol. And then the laser actually burned a hole in the entrance window. But that's fine. I mean, because the liquid the surface tension will keep the liquid inside. So that doesn't really hurt the experiment. So
But burned a hole, we mean ruined the coating on the mirror?
no, it's actually drilled a hole.
How thick is the glass?
The glass from here, I think it's like typically 3 millimeters.
Burned a hole through that.
So, and then that's the white light. So using this cell, he was able to convert about 80% of pump into the amplified Stokes. So I think that's and then the next step was to work on the system to use the gas chamber. Our next move is to get the system taken back here. And this is Dr. Fry's lab at the Mechanical Physics Engineering building. It's a very large lab. I mean, this curtain this part in curtain, inside the curtain, and host. This is probably an 18 feet table. And there are two sessions of this space. It's very large. I mean, I think this two session is larger, actually larger than the session lab we used in brick. So it's already like a clean room space for optics.
So it's even bigger than Sukever's lab at Princeton.
I've never been there. So. and
It is, isn't it? Sukever's lab, remember, had 2 rooms. And I think this is bigger than those 2 rooms put together. My perception.
And another good news, but we haven't checked it if it's still working on it. Hopefully it's working. It actually has a HEPA filter system already installed in place in these two space. So, oh yeah, that's the problem. So this is where we are. The system in Baylor, well, we intend to move it into this space, but of course there are a lot of laser systems in that room. Some of them are working, some of them are not working. We know they're not working. Some of them are not sure if they're not working or not. So I think that's all the contents of my talk, and the main reason is to facilitate a discussion, so I can bring everybody onto the same page, so that we can develop projects with the system and also recruit students, postdocs, and especially a leader in this project.
To gauge the applause this man deserves, we went to him a week ago and we said, hey, we got to move the Baylor experiment. We need somebody to join us. Would you give a seminar? So he just put it together, back of the envelope, beautiful talk. Thank you very much.